So this is a video on the review of section 16.3 on the fundamental theorem of line integrals. So we are only going to do a review because we have already done this in Calc 3 when you did Calc 3. So all it says is that basically, so this is a line integral, f dot r, right? And then in certain circumstances, the way you usually evaluate it is you parameterize the curve and then you evaluate it as a normal integral, right? Once you parameterize the curve using a parameter t or something. But sometimes if the curve is a little complicated, it's difficult to do that. So, what it says is that in that case, if it happens that the vector field in concern is a conservative vector field, which means is the gradient of a potential function f, then the line integral is simply the potential function evaluated at the endpoint subtracted the potential function evaluated at the starting point. So let's start with a question, right? So we need to evaluate this. So now by definition itself, so we need to evaluate a gradient f dot date gradient dr, right? So by definition, right, we do have the vector field is a conservative vector field, and the gradient, the potential function is small f. So then the line integral really reduces to the value of the small f at the endpoint minus the value of the small f at the beginning point. So we know we really don't want to parameterize the curve or anything like that. We only need to know the beginning point and the end point. So what you do is you evaluate the potential function at the end point, subtract the potential function at the beginning point. Okay. So when you evaluate the potential function at the endpoint f2, 1, negative 1, what you need to do is to go to the potential function and plug in x equals 2, y equals 1, and z equals negative 1. So if you plug in x equals 2, then this one right here becomes cosine 2 pi, and then with y equals 1, you get sine pi, cosine 2 pi minus sine pi minus xyz would be the product of the coordinates 2, 1, and minus 1. So in the end, cosine 2 pi is 1, sine pi is 0. So 1 plus 0, and you get minus 2, which is plus 2. So that is 3. So similarly, you can evaluate it at the starting point by plugging x equals 1, y equals 1 half, and 2. So x equals 1, which is cosine pi plus y equals 1 half sine pi over 2 minus xyz, the product, which is 1 times 1 half times 2, which is 1. So minus 1. So you get negative 1 plus 1, which is 0. And then you end up with here you get negative 1. So that's negative 1. So really the difference between these two, the endpoint, the value of the potential function at the endpoint is 3 minus 1, which is 4. So this is the value of the line integral. So to give a more complicated example, so here it's kind of easy because you are straight away given the potential function, right? Because you know what the potential function is. The potential function is, given to you as cosine pi x plus sine pi y minus xyz. But sometimes you need to find the potential function, right? And then, so if you have a integral like this, line integral, so first of all, you need to find out whether it's conservative, and there's a simple check for that. You know that if you take this part p and this part as q, and if you take partial of p with respect to y and partial of q with respect to x, so partial of p with respect to, so p is this, the coefficient of I, and q is this, the coefficient of j, and if you take the partial of p with respect to y, you get this, and you take the partial of q with respect to x, you get this, and you can see that they are equal. Actually, this should be down here really. So you can say that the partials are equal, p with respect to y and q with respect to v. That means a conservative vector field. And then we would have learned techniques in Calc 3 how to find the potential function. So what you do is you take this and you think of it as a kind of a differential equation, and then you take the integral with respect to y, and then you take the integral with respect to y, you think that 8x cube, and then y cube is a constant, so 8x cube is a constant, and then y cube becomes y to the 4 over 4. But then, there could be, you know, uh, so y to the 4 over 4, but then there could be a constant which is a function of x alone, and then you just do it differentiate it again, and then you find that constant, and then and so on and so forth, and finally, with that type of approach, you can actually get the small f or the potential function as this. And so I leave it to you. I can send you a video if you want to do an example where you find a potential function like that. But this is only a review video, right? So what you do now is that because we know that this is conservative, right? The value of the integral will be the value of the potential function at the end point minus the value of the potential function at the beginning point. So how do you find the endpoint now? So this is the parameterization, t going from 0 to 1. So the endpoint you find by plugging in t equals 1. So you get 1 times cosine t minus 1. That is your x, right? Okay, and so that is cosine pi minus 1 is your x, and the y would be the sine, put t equals 1, you get pi over 2, right? Okay, and that is your y. This the end point minus the starting point. You just plug in t equals 0, and then you get 0 for minus 1, so negative 1 for the x, right? And then when you put t equals 0, the whole thing goes 0, so negative 1 and 0. So evaluate the function at negative 1 and 0. So when you do that, you get this, right? And then and you calculate the value of the potential function and subtract the two, you get 10. So the answer is that, so the value of the line integral is actually 10. And once again, here the only difference is that we had to actually physically find the potential function before evaluating the line integral. And so this is only a quick review video for that. And thank you for watching, and we will meet in another video soon. Thank you.